photon of electromagnetic radiation incident on an electron, then the energy absorbed by the electron is known as absorption of the photon. So what happens is
Okay.
it
Yeah.
gets excited to the next energy level. Okay, but when
Mm-hmm.
the electron wants to come back to its previous energy shell, or you can say lower
It
energy shell,
emits the photon.
yes, it emits
It
it.
emits a photon. Okay. Yeah,
That's
that makes
right.
sense. Mm-hmm.
Okay, so how can you define excitation? And what's the difference between
Excitation.
excitation and ionization? Okay.
So excitation is when an electron gains energy and moves up to another energy level. Moves up an energy level.
Okay.
And ionization is uh, the gaining or losing of electrons.
So ionization, yeah, but it happens is ionization is basically that electron gets detached from the shell.
Yeah. Oh, sorry. Yeah. Okay.
Because
Yeah.
otherwise
So
ionization and excitation will be the same. Okay.
same thing. Yeah.
And what do you mean by ionization energy?
It's the energy required to take electron from its ground state to infinity.
Yes, that's good. Okay. Now we study line spectra and continuous spectra.
Okay.
Okay. So for line spectra, we can define as, take the example of light from a fluorescent tube. So it produces basically a spectrum. Spectrum is what? The combination of light. Okay. Like
Mm-hmm.
if we say electromagnetic spectrum, so it's a combination of electromagnetic waves. Same as
Yes.
the spectrum is basically the combination of the waves. So when it
Mm-hmm.
produces a spectrum of colored lines on a dark background, so there are the colored lines you can see, but on the black background or in the dark background, such pattern of lines are known as a line spectrum. Okay.
Okay.
So generally,
Mm-hmm.
we get such a spectrum from the fluorescent tube and LEDs, something like that. Okay. So these are the energy sources from which we get a line spectrum.
Okay.
And if we say it's continuous spectrum, so the light that we get from the sun or from the filament lamp, they gives a continuous spread of the colors that merges
Yes.
into each other also, because they are actually
Mm-hmm.
not, you can't see them distinguished. Like even if you see a rainbow, definitely you can see the colors, but like there is no separate line in between them. Suppose
Yeah.
this is
Okay.
violet and indigo, so you can distinguish where's the line where they get separated. It may be violet up to here, but then this is the portion where the both color are merging. Okay.
Yeah. Okay.
So
Okay.
such spectrum are known as continuous spectrum. There is a continuity. There is no breakage in
Yes.
between them. So such are known as a
Mm-hmm.
continuous spectrum. Okay.
Yes.
And this happens because of the diffraction. So like, do you know what is diffraction?
That's where uh, light, because the photons travel, well, they're different wavelengths. They diffract at different
Yes.
angles, and then it gets yeah,
Yes.
basically splitting
Basically,
up of light.
yeah. So basically, that kind of you can say as diffraction. So diffraction is because of the diffraction we can see that spectrum of the light, whether it's a continuous or the line spectra, is because of the diffraction. Okay.
Mm-hmm.
Now there's emission spectrum. So moreover, you can say bending of the light, but not just, but more specifically around the obstacle. That's more accurate to define as diffraction.
Okay.
emission spectrum or spectra. You can see such a spectrum when electrons in an atom fall from higher energy level to lower energy level. Okay,
Electrons.
it has nothing to do with the diffraction or else.
So electrons from atoms drop.
From higher energy level to lower energy level, and in this process releasing the photons.
Yeah, that makes sense. Lower. Okay.
So example is mercury vapor. So electrons
Okay.
in a mercury vapor, electrons can take a small number of discrete energy level. Okay,
Mhm.
and when gas is heated, electrons absorb energy and reach to higher energy levels, and when it cools down,
Oh, I see. Yeah, that makes sense. Okay.
and electrons stay there for a while in the excited
Yeah.
state, but then when they lose heat, it falls back to its lower energy level.
Yeah.
So when
Mhm.
electron falls to its lower state, in this process it gives off a photon, and its energy is equals to the difference in energy between two energy levels. So suppose
Yes.
this is the first energy level and this is the second energy level.
Mhm.
So when absorbing energy, this electron jumps to this, but after losing the heat, it goes back to its initial state, and this energy is actually equals to the difference in energy between these two energy levels, because each energy level has its own energy. So its
Mhm.
energy is equals to difference in the energy of these two shells.
Yeah.
Okay.
Okay. Mhm.
So such spectrum that we get, that means when an electron gets back to its initial state or ground state releasing photon, the spectrum that we get is known as emission spectrum. That's why it has its name emission.
On a mission. Yeah. Mhm.
Okay, and then in this process, the photons that are emitted, they have a specific energy, and because of that, they have a specific wavelength and a color also.
Yes. That's right. Okay.
Now, it's the absorption spectrum.
Mhm. That's just the opposite.
Yeah.
So where it absorbs the photon. So instead of having what certain lines, you just have gaps.
Yes. So like
Okay.
it's when and there is a dark lines on the spectrum corresponding to the
Yeah.
wavelength that they absorb.
Yeah.
So such a spectrum is known
So
as absorption.
electrons. So when electrons um,
So when electrons in the atom absorb the
get
photon,
excited,
yeah, it absorbs the photon and get excited.
yeah, photon and gets excited, jumps. Um, yeah, cool.
So have you written it?
Yes, I've got that down.
Now let me see the energy of the spectral lines. So when electron moves to lower energy level, it gives a photon, that's obvious. And this is equals to
Mhm.
what? The difference in the energy level. So this is equals to,
Yes.
suppose E1 and E2 are the two energy level. So this is E2
Mm-hmm.
minus E1 equals its energy, which is, okay.
Oh,
So
okay. Yeah. Yeah, that's right. That makes sense.
so E1, E2 are the energy levels of level 1 and 2. and h is the Planck's constant, and f is the frequency of the radiation in hertz.
Yes. Mm-hmm.
Okay. Now, if I draw a spectral array, this is for n equals 1, that means for the ground state, and for n equals 2.
Mm-hmm.
This is for n equals 3, 6, 4, 5, 6,
Mm-hmm.
and so like that up to infinity.
Yeah.
For n equals 1 is minus 13.6 electron volts.
Why is it minus?
Why it's negative? Because it's
Mm-hmm.
the first energy
Oh,
level.
yeah. Okay. Okay. Yeah.
Because the ionization energy is total 13.6 electron volts. Okay,
That makes sense. Okay. Yeah. That makes sense.
so this is minus 13.6 electron volts at the ground state. Then,
Yes.
as we move on further, it's n equals 2. This is 3, 4, 5,
So
6.
13.6 electron volts is how much it will need for it to.
That means
Uh.
this is actually it's a spectral line of a hydrogen atom.
Yes.
Okay,
Oh. Okay.
and
Yes.
for hydrogen atom, it's a 13.6 electron volt and energy is required. That is, this is known as what? It's energy
Ionization.
ionization energy. So
Okay. So
this
to
is
leave the
atom
atom
completely.
altogether.
Yes, to
Okay.
leave it.
That makes sense. Cool. That makes sense.
Then it's n equals 2, which is minus 3.41 electron volts.
Oh, okay. Mm-hmm.
Then it's minus 1.5 electron volts. Now it's negative 0.85. That's negative 0.54. And this is negative 0.38.
Negative 0.54. Negative 0.38. Okay.
Okay. Now these are the errors. These arrows indicate that they are moving, like electrons are
Yeah.
moving downwards.
Going from, yeah. Okay. So they're losing. So
Energy.
they're emitting.
Yes.
Yeah. That's fine.
Okay. Now this is the these are the energy levels, and if the question is use this figure to calculate the frequency of photon released when an electron moves from energy level 9 equals 6 to n equals 2, sorry, n equals 6 to n equals 2.
Okay. So energy levels from 6 to 2.
Yes.
Okay. So uh, E. What we're working out? The frequency.
Uh, No, it's the yeah. You have to calculate the frequency of a photon.
Frequency. So energy one minus energy two minus energy one equals hf. So 6 is 0.3. Um, this and 2 is 3.4. Hmm. So divided by 6.666. 6.666 that's G4. So is the frequency 4.57 times 10 to the 33?
No, it's 7.3 into 10 to the power of 14 hertz. Okay, so it's that you have to do what? The energy of the photon is the difference in the energy level. So difference in
And
the
but do I have to work out energy in joules then?
yes, because if you're using
Yeah.
Planck's constant, so yeah, it should be.
Yeah. Yeah. Just joule seconds. Just whatever. So time 1.6 times 10 to the 19. 1.6 times 10 to the 19. Makes sense to why it was a diffusion of that stuff. Is it 7.3 times 10 to the 14?
Yes, that's correct.
Okay, that's fine. Yeah, that's fine.
Okay. Now, hmm, it's taking time to upload with that as of now. So
Oh,
let
that's
me
right. Yeah,
start this one. So photoelectric effect. But we'll do questions on that, okay? But as of now, I'm just covering this
yeah,
one.
that's fine.
So do you have any idea of photoelectric effect?
So that is that the one where you have two gold leaves, a plate of zinc, and then you when you put what's it called? UV light on the zinc plate, the gold foil gets back together.
On a negatively charged gold diffraction crystal, yeah.
Yeah, sorry, yeah. Yeah.
Yes. So actually, why we use ultraviolet light? Because it's a weak source. Okay.
Yeah.
So when it's directed to the zinc sheet, the electroscope discharges it immediately. So it's an
Uh-huh.
electroscope that we use of that contain the gold leaf. Okay.
Yes.
So yeah, you were
Okay.
saying something. Continue.
So, so what is it? So, got a negatively charged plate, and you have two. So you've got a gold leaf, or two gold leaves that are the same charge. So they repel at the start, and then as the UV light knocks off the electrons, it becomes less charged and come together again.
And so basically, this is an experiment to show the photoelectric effect. And when you incident, or you can say ultraviolet rays of this electromagnetic wave,
Mm-hmm.
ultimately at the end of this whole experiment, we get to know that this ultraviolet ray can knock the electron out of the metal surface. And this
Yes.
actually is known as photoelectric effect. So in short, this is what an experiment, but if you have to define a photoelectric effect, so you can see that a photoelectric effect is the phenomena when photons hit a metal surface, it can delocalize the electrons, removing them from the electrostatic force holding them in the metal. Okay. So actually what happens is it's the electrostatic force that holds these electrons together inside an atom or inside a given metal surface. But photoelectric effect is what? When a photon of high energy hits a metal surface, it just passes its energy into the delocalized electrons and removing them from the electrostatic force or removing them from the metal surface. Simple. That's the photoelectric effect. Is this clear?
Yes. So it's photons delocalizing electrons
Removing them from the
from from a metal surface.
yes.
In
That
simple terms. Okay.
effect is known as photoelectric effect.
Yes.
Now, the important thing is only high frequencies can carry enough energy to overcome the work function of the metal. Now, there is a term that is known as work function. That's very important. Okay.
Well, function. That's the Okay. Cool. That's fine. Yeah.
So let me define the first definition is what that photon when
The
emits an electron
photoelectric.
from the metal surface is what the photoelectric effect. That's a simple
Yes.
definition. Now let me
Mm-hmm.
see what is work function.
So work function is the minimum energy required to release an electron from the surface.
Yes, that's very correct.
So to knock the ones that are in the highest energy in the shell.
Yes. So that's why I say
Okay.
only high frequencies can, that means photon carries high frequency can do that. The lower frequencies, they are not able to because they have to overcome the work function. Their energy should be greater than the work function. Then
Mm-hmm.
only you can see photoelectric effect. If the emitting
Okay.
photon or incident photon has lesser energy than the work function of metal, then there will be no
Nothing
photoelectric
happens.
effect.
That's right. So that's why it doesn't work under light,
Yes.
visible light.
Yes.
Okay.
Okay.
What energy required to delocalize electron surface? Okay.
Then there is a term that is known as threshold frequency.
Mm-hmm.
So what do you mean by threshold frequency?
Yeah. So that is the minimum amount, the lowest frequency of light. The
Hello? Yes, you were saying something. I was just disconnected. Yeah, you were defining threshold frequency. Can you just repeat that?